So in this R&D lab, I'm usually doing measurements, or doing setups, and we'll kind of get to that. So this is actually a new addition to our lab. This is a near-field scanner robot. It's made by a company, Klippel in Germany. This is a really nice addition because this does automated measurements. It also does automated anechoic measurements. So using this system, we can put a speaker on top of it and then measure, if it's a simple speaker, maybe 1,000 points. If it was just low frequencies, maybe a couple of 100 points all the way around it. For something complex, it might be 5,000, 6,000, 8,000 measurements or something. I might let it, run overnight for 12, 16 hours or something. So it measures in the near field close to the speaker, and it measures 2 different cylinder sizes. And because it knows those 2 different sizes, it can pull out which sound is traveling outside of it and which sound is traveling back into the microphone. And so now that it knows that there's sound coming in or out, it knows which are room reflections and which actually originate from the speaker. And so it can pull the room reflections out, and that's how we can get anechoic data with it, which is a huge advantage because traditionally you'd have to build an anechoic chamber. If we want to do something like that, we would actually literally have to build a separate foundation from the rest of the building. It'd be double wall thick with concrete blocks and creating air spaces. It'd be massive. We'd have to, shoot the speaker to the mic 4 or 6 meters away. It'd be really large. It would cost, in today's dollars, it's probably more like $4 million. And it used to be a little bit less or whatever, but there's just so much construction and land cost and everything that it's a huge endeavor to do that. So this system is much cheaper, and it has several advantages that the microphone's closer, so the signal-to-noise ratio is better. But basically, it's getting speakers on here, doing automated measurements, measuring transducers individually, and capturing the total sound power of the speaker. Because what we're really interested in is knowing, okay, not only the on-axis sound, but what is all the off-axis sound going to be? So what else is getting sprayed into the room? What's getting reflected off of walls, or potentially floors or ceiling? And how those late reflections come and contribute to the tonality and the sound that we hear. So from a design perspective, for me, it's more of understanding how the individual passbands work and also how I would, configure or align the crossover. So how are we going to get a smooth transition so we don't have so much lobing off axis, and smooth out the response. So it's used, for checking, but then eventually it's used for like creating presets or speaker profiles, and updating all that.
What Steven does a lot is takes an individual driver, measures it, has to understand how it works, then put it in a cabinet, put it with other drivers, so you start to build up a full speaker. And having all the individual measurements, you could imagine if you took 2,000 measurements in your room, you could really understand everything that's happening. It's really hard to do that without some kind of automated system. So this lets us get a lot more fine detail than we could before, and hopefully get better sounding speakers faster, and just speed up the whole process, but also just have a better quality product.
Yeah, and also helps me do like virtual product development. So I can measure the transducers in this cabinet separately. This doesn't have a passive network, but I could just on a computer simulate a passive network, or I could simulate dozens of them and rapidly go through and see how they work, as opposed to like an old style of working where I would just sit here with inductors and capacitors and swap them out and take a single measurement and go, does it look a little bit better? I don't know. How does the off-axis look? I don't know. I'd have to keep positioning the microphone. So it helps to do a bit more virtual product development in a computer, simulate things, and then verify the results afterward. I mean, with that, it's not really necessary in this case, but to that point, it would be more building a prototype and then, probably just moving to the next area. So
one of the things that, and this is just kind of showing a real simple version of this. So subwoofer, which is just a single driver, obviously. One of the things that we'd asked Steve to do was, we have this nice, really slim 10-inch woofer, sealed box. Could you make something that went in the wall and, what's the possibilities of what it could sound like, what's the performance we could get. So this kind of just shows that progression, starting with just basic measurements of the driver itself. And I'll let Stephen explain this because I don't understand any of this. This is all very complicated.
I like the colors.
The colors are very nice. I like the colors. They're beautiful.
Yeah.
So then taking it and modeling it is the next step. And that's what he's saying is, instead of trying to build it and measure it, and you got to build, how many are you going to build? 10, 15, 20. You can model, hundreds because you have all the data.
So this is these are just pictures of a BEM model. So it's a boundary element model. It's a form of finite element analysis. And with boundary element, all you do is draw the actual boundaries. So you can kind of see this is the model that there's like this yellow portion. It's just all triangulated. So the green and these colors of these panels is just saying that green is one amount of damping and yellow is a separate amount of damping because there's actually damping material in it. And this model is of this prototype. And I had designed this larger prototype first. And the question was, what can we do after that? But this is more traditional transmission line, but it's a front-loaded transmission line where the driver is actually directly radiating, and then the transmission line is in the box. And so there's actually, I kind of drew where there's interior panels, and so these wrap around, and this driver is offset from this endpoint. It actually wraps around the bottom and goes into this stub, and then the rest of the sound travels along the rest of the path and comes out. And the benefit to moving this driver from one end of this, tube that it's trying to radiate through is that we can control the first anti-resonant mode, because this has a fundamental mode. So just like a vented enclosure, it has a fundamental frequency that it operates with. But then above it, there are resonant frequencies that we don't want. We want that first one because it gives us the low bass, but we don't want the rest of them. And so the tuning frequency we can see, and the color is a little hard because it's actually consistent, is there's a consistent sound pressure. There's just a plane in the middle of this box that's showing the pressure off of that virtual face. It's not a real face or anything. So you can just see that there's pretty constant pressure, and then it's just going down in pressure as it goes to the exit, because it's going to turn into velocity and actually shoot the bass out of the fort or whatever. But the real trick is picking the line length. So this stub, and this is at 87 hertz. So the tuning frequency about 23, 22 hertz. And this first mode that wants to happen and cause a cancellation is at 88, upper 80s, 90s. And you can see it's all red. It's very high pressure in this stub area, and it's very low pressure at the woofer. And this is actually now a mode that's trapped in the box, and it doesn't allow this mode to escape out the vent, because otherwise there would be, positive sound pressure from the woofer, and it'd be a negative pressure coming out of the box because the back of the woofer is back there, right? So it'd be the opposite polarity. It would want to cancel the sound out. But because this is designed this way to have this offset stub, it creates an internal standing wave that actually cancels that mode out. So now we can get it so that the subwoofer box wants to operate, much closer and farther above, where we want it to go to. So using an 80 hertz crossover with this is going to be much more feasible rather than having a big, anti-phase dip right where we're trying to cross over.
And really the idea is just to get to something at the end that's better, do it faster, ultimately be able to come out with more products that we, are to our standard, and spend less time, building, prototypes, because that's really not beneficial. That just proves whether or not it works. But you can't get that much out of it. I'd like to do is just take a step back and kind of explain what a planar magnetic driver is. Does anybody know for sure what it is? Okay, good, because even I am always a little sketchy on it. Because we talk about it a lot, and you'll hear it over and over and over again in the presentations. Planar magnetic, and this, and it's a core technology for wisdom. So it's a good idea to just really understand what we're talking about. And the first thing you have to really know is, what is a speaker in the first place, right? What does it do? How does it work? So in a really basic model, all this out of the way. So this is, and you'll have to get a little close to see it, but this is a big magnet, and there's just a little piece of wire here. And I have a 9-volt battery. So really simple. This is basically 3 parts. And if I use the battery as my energy source, as my voltage source, let's see if I'm going the right way. You can see I can make it move. I don't know if you can see that from back there. Oh, you guys see that? Okay. So what's happening is, by passing a little bit of current through that wire, it's interacting with the magnetic field, and we can make that wire move. And that basic principle is every speaker that's out there, everything that you make it move, you put some power through it, some energy, it's got some magnetic field, makes it move, you make sound. That is the basic concept of every speaker. Microphones work the exact same way in the opposite. So you talk into a microphone, it makes a thing move. There's a little piece of wire, there's some kind of little magnet, it translates that into an electrical signal. So it's just the exact same thing. So what is a planar magnetic? So here is a disassembled woofer, one of these woofers. And again, there's a magnet in the back. There's a coil of wire in there, right? So it's the same thing, same basic parts. We've taken off the front half. So normally there would be, this cone, which would be attached to the coil of wire, so that when the wire moves, it pushes on the cone. So we just took it off so you could see it. And the same thing will happen if I, let's see, you can see I can make that move. That's what's happening inside the speaker. So that would probably sound really bad, but I don't know, that's, dance music or something. But you can see that just by having a magnet, now we've got this coil of wire, we attach it to a cone, we can make it move, it's going to make sound. We call it film. It is essentially a really thin material that you can deposit. This is aluminum traces. So here's our coil of wire, we've just flattened it out, and we have to put it on something. So in the woofer, it's actually on this little round cardboard former. In our planar magnetics, it's on this film, but it's the same thing. So we've got a coil of wire, which we've now flattened, and we've got our magnets, which are, instead of being a round magnet, they're just bars, so they're flat. And when we have our coil over our magnet, now we've got the magnets and the film, they're in the same plane. So it's a planar magnetic driver. Mystery solved.
By the way, if that was a traditional tweeter, it wouldn't be working right.
Yeah, we would already be dead. So you can see, just by putting it in a configuration with the magnet in the right position, it plays a lot louder. Okay. Is it really annoying?
It is.
It is. Which helps to increase the strength of that field. And if I get it in the right position, you can hear it start to get louder.
Yep.
All right, so it's just that efficiency, just by having that extra magnet. And these are really small but really powerful. I always like to let people try and just put this on top of that, one-handed. Go ahead. And it's a really small magnet.
Do you remember when you were a kid, you played with magnet?
Yeah, I played, but
Yeah,
Try to
you'll
get
never
the
get it
bounce.
on.
Put
No?
it on.
Yeah, try.
Oh no.
oh yeah, it's
Oh, you're drunk.
opposite poles.
It's always pushing you away.
Yeah, yep.
So it's actually a very, very strong magnet,
Yep.
even though they're small. And one of the nice things about the way the film and the magnets are arranged is that there's a lot of surface area, there's a lot of exposed area. So one of the reasons that that's a benefit is that it naturally gives us something that can take a lot of heat and still keep playing, right? It's got a natural cooling effect to it, versus being sunk behind the woofer, where this whole thing becomes a heat sink and it just holds that in. So things get hot, even in a tweeter, it's behind, so it heats up, eventually gets too hot, and it stops working. So that's one of the big enemies to any driver, whether it be a woofer or a tweeter. So with this one, because it's exposed, I do need a volunteer. Anyone? So this is just a instant read thermometer. It won't hurt you. So if you just push the button and get the red dot. So what's the temperature?
73.8,
Yeah,
74.1.
so get right. So that's basically the temperature in this room, right? It's ambient temperature.
It's not hot.
I'm going to turn the frequency up, and I'm going to turn the volume up, because otherwise we would all go deaf. Okay, can anybody hear that?
No.
Okay, good. It's also an age test. So I'm going to turn this up, and just tell me when it starts to heat up.
You can go 79, 83, 85, 86, 93, 99, 100, 104, 117, 122, 126.
So what you'll see is this is actually going to start to deform a little bit, the aluminum. Yeah, keep getting on. Still heating up.
132, 135.
Ready for that?
How far it can stand up.
I don't know. I've never actually pushed it to the limit. What'll happen is actually the glue that holds the aluminum to the film will delaminate first. So if you see a failure, usually what you see is the traces are pulled away from the film. If you look at a blown PMD, that's what you'll see. Is there's like pieces of aluminum just sticking off because the glue is actually let go. I don't know. I can't remember what the temperature is. It's pretty high.
So in real time, how much volume we can go up to? Wattage?
140.
It all depends on how many and what else it's the crossover. So there's not one answer off of it.
Yeah.
Go for it. Won't hurt you.
Yep.
And so if I do this, yeah, we're right around 200 degrees. So I'm going to turn this off, and almost immediately you'll see it goes back into shape, and it's already coming back down under 100 degrees. It's going to start cooling off pretty quick. And it still works just like it did before. All right, so we sat there for a few minutes, letting it just literally radiate heat, and it still works just fine. So that's one of those benefits of the PMD. And this is just a little DC power source, so it just pushes it out so you can see it, and it's not going to keep moving. And all right, so that's about the maximum that I can get out of that woofer. Right, so you can imagine if that was playing. And it's a pretty good woofer. The problem is that it doesn't have enough dynamics and enough output to match what we have in the PMDs. So if we look at something like, this is the woofer that's in like S90s and SCS, yeah. So similar kind of surface area. You can see it's got a much beefier magnet in the back. It's also much heavier, so it's good. It's a good workout. And you'll see the difference. It's got a lot more travel in that woofer, and this is actually not even. This is just the maximum of this power supply. I could give it some more, and it would continue to move. It's also a pretty strong woofer, and I don't. All the sales guys love this, and it's kind of fun, but I'm not sure exactly.
We just love it. Okay?
We just love it. We just love it. But it's strong enough that it actually can lift itself. So it's a very, fundamentally a very strong, stiff woofer, but at the same time it's got a lot of travel, and you can see how heavy that is.
Pass it around, yeah. So you see the weight, right? It's a lot of force to move it up, right?
Yeah. And the other woofers, so this is a Sage woofer, so again, like C38, P38, and this is the Insight woofer, so if you were looking at the like P2i and P4i, that's what would be in there. And they're all very similar designs. And they can do, again, similar kind of travel And you can see in this one, it's actually inset really far back, unlike something like this where the surround is basically level with the frame. In this, it's actually pretty deep in there, because with this one, what we found is the grill was getting pushed off because the woofer was actually moving so much. So we had to inset the cone into the frame to allow for that extra travel. So it's little things like that kind of go into coming up with something that's somewhat unique for Wisdom and is not necessarily needed on maybe other companies' designs, because they don't really have that dynamics from the